Hello, Math 1224. This is Dr. P with Lesson Launch 502, Profiting from Sin. Gosh, what could that be about? Well, this is a pun like most of the titles of these videos, but you'll see soon enough what that's alluding to. So this video is going to be an example of the last major integration technique I'm going to teach you. We now have all these different ways of integrating. We have substitution, we have parts, we have the integral table, which really has a lot to choose from. There's not a whole lot in the world that we can integrate analytically but can't use the integration table on. And there's also partial fractions, so what could possibly be left? Well, I'm going to show you an example of an integral on which I don't think we can use any of these, but there is a nice little technique for handling it. Okay, so here's the example I want to do. Suppose I want to compute the integral of dx over 9 minus x squared to the 3/2. Now that's an interesting one. We got a 3/2 power. I don't think you're going to find that anywhere in the table. So the idea behind what I'm going to do here is this expression 9 minus x squared seems to figure prominently here. And if I were to just set out and make what would seem to me to be the most obvious u substitution, u equals 9 minus x squared, I would get du equals negative 2x dx. And I have a dx up there, but I don't think I have any negative 2x, so I don't think I can get anywhere by using this particular substitution. Alright, so what else could I try? I mean, I've got all these different techniques here. I don't see this as a particularly good candidate for parts. I just don't see any way of decomposing this integrand as u dv in such a way that I could integrate the dv but differentiate the u and expect things to come out any nicer. You can look over the integral table yourself. I don't think you're going to find anything quite like this with a 3/2 power. And because this is not a rational function, it's just not a good candidate for partial fractions. I can factor the 9 minus x squared, but then after that, it's not going to be possible to come up with a partial fraction decomposition with this exponent of 3/2 here. So I'm going to have to try something entirely different. So again, example I'm working on here is the integral of dx over 9 minus x squared to the 3/2. Now I'm going to focus my attention here on this expression, the expression inside these parentheses, 9 minus x squared. If only there were some way to make that simpler. Well, one way that I could make it simpler would be if x represented something which, when subtracted from 9, gives me something that has only one term. So what if I were able to make x squared, and this is going to seem totally out of the blue, what if I could make x squared equal to 9 sine squared of theta? Alright, that's got to sound like a crazy idea if you've never seen this before. But what if? If that were true, then it would follow that 9 minus x squared is equal to 9 minus 9 sine squared of theta, which would be the same as 9 times the quantity 1 minus sine squared of theta, which is 9 cosine squared of theta. And you'll see why this might be an improvement in just a little bit. I mean, you can probably start to see it now. If I were to take this and substitute it somehow for this quantity here, the part being raised to the 3/2 power, well, that would raise to the 3/2 power pretty nicely because I can take the square root of that no problem and then take the cube of that. Now, in order to do this, I've got to set the table properly here. I need to do a substitution that would allow me to say that x squared equals 9 sine squared of theta. So what I'm going to do is use a special type of substitution here called a trigonometric substitution. So I'm going to use the substitution where x is equal to 3 sine of theta. That's what would make this true, that x squared equals 9 sine squared theta. I'm going to let x equal 3 sine theta, and then that's going to make dx equal to 3 cosine theta d theta. So if I use that substitution in my integral here, I'm going to get, well, dx was 3 cosine theta d theta, and that's going to be divided by 9 minus x squared, that's 9 sine squared theta, to the 3/2. And then what's all that going to come out to? That's going to be equal to the integral of 3 cosine of theta d theta over 9 cosine squared theta to the 3/2. Okay, now remember, 3/2 power of something means take that thing, take the square root, and raise that to the 3rd power. So I'm going to get integral 3 cosine theta d theta, and then that's going to be the same thing as 3 cosine of theta to the 3rd, which is going to equal the integral 3 cosine theta d theta over 27 cosine to the 3rd of theta. Now at this point you might be wondering whether things are getting any better at all. I've got a whole bunch of cosines in here, and I'd started with something that didn't have any trig functions at all. But here's where the magic happens. If I simplify that, I get 1/9, which I can pull that outside the integral if I want to, times 1 over cosine squared theta d theta. And then that can be rewritten as 1/9 times the integral of secant squared theta d theta. Now, think to yourself, why in the world might it be advantageous to have an integral of secant squared theta? When you think about it, that's a very recognizable function in calculus. That is the derivative of the tangent function. That is 1/9 tangent of theta plus c. So if I pull out here, there's the entire calculation at once there. This tells me that the antiderivative of all this is going to be 1/9 of tangent theta plus c. Now, we can have an argument over whether I've actually improved things. Right now, I'm not sure this is an improvement. I've got an answer which is in terms of theta, and I would like to have an answer in terms of x. So we need to figure out some way of getting this back to something in terms of x. Okay, and what we know right now is that x is equal to 3 sine of theta. That doesn't tell me necessarily how to write tangent of theta in terms of x. For that to happen, I'm going to use a little technique that I like to call the magic triangle. The magic triangle. And the purpose of the magic triangle is to tell me, if I know, for example, that x equals 3 sine of theta, what does that make tangent of theta equal to anyway? All right, so the first step of this process is to draw a picture of a right triangle in which I have some angle theta such that sine of theta is equal to x over 3. Because I want to have x equals 3 sine theta, that means that sine theta needs to be x over 3. So I'm going to draw a right triangle. Sorry, not the most convincing right triangle there, but this is really just a schematic anyway. With an angle of theta, angle of measured theta. And if I want the sine of that angle, or the sine of that angle measure to be x over 3, one way I can achieve that is I can make this the opposite leg of the triangle, x, and make that the length of the hypotenuse. So I'm going to let that be 3 and that be x. Okay, and then the question is, what is tangent of theta under these circumstances? Well, the tangent of theta is going to be the length of the opposite leg over the length of the adjacent leg. Well, I have the opposite leg's length, that's x. But what is the length of the adjacent leg? Well, to get that, I use the Pythagorean theorem. I get that the length of the adjacent leg is the square root of 9, it's 3 squared, minus x squared. that's my adjacent leg length. So the tangent of theta is going to be the opposite leg length, which is x, over the length of the adjacent leg, 9 minus x squared. So coming back to this final antiderivative here, I can finally write that as 1/9 tangent of theta, which is x over square root of 9 minus x squared, plus c. Not the most elegant answer you've ever seen, but I think that if I were to take the derivative of that, I would get the function I started with originally, which is 1 over 9 minus x squared to the 3/2. I invite you to try it yourself. This one is not the worst one to take the derivative of. We've seen ones where if I asked you to take the derivative, you'd probably tell me to forget about it. But this one, you could actually take the derivative, use the quotient rule, and verify that the derivative is equal to this. So anyway, that is an example, the first example for us, of trigonometric substitution. The idea is not really any different from what we did when we were doing U substitution a few sections ago. The main difference is we're now introducing trig functions where there weren't any, because we see an expression like this that might be made simpler by the right trigonometric substitution. Here, the whole idea was if x squared were 9 squared theta, then this simplifies down to 9 cosine squared theta, and in this particular case, that happens to make things easier. So anyway, that's an introduction to the technique of trig substitution, and that's it for now. We'll do a little more detail on when certain trig substitutions are useful when we return to class on Wednesday.